High-mast lighting poles require a proper grounding system. The reasons and requirements are as follows. Firstly, lightning protection is paramount. The lightning rod on the pole intercepts lightning strikes and diverts the current to the ground. To ensure effective lightning protection, the lightning rod must be properly grounded to provide a low impedance path for the lightning current. Secondly, equipment grounding is necessary. The electrical equipment in the pole, such as luminaires, ballasts, and wiring, must be effectively grounded to protect against electrical faults. An equipment ground conductor is connected to the metal enclosure of the equipment and the grounding system. Thirdly, personnel safety is enhanced. A proper grounding system provides a safe path for fault currents, preventing them from flowing through individuals who may come into contact with the pole. This is especially important for high-mast lighting poles, which are typically accessed by maintenance personnel. The grounding system for a high-mast lighting pole typically consists of several components. 1. Ground rods are used. These are long, metal rods driven into the ground at a predetermined depth and spacing. 2. A grounding wire is installed. This is a bare copper wire that connects the ground rods to the pole base. 3. An equipment ground conductor is implemented. This is a wire that connects the electrical equipment on the pole to the grounding wire. 4. A lightning rod connection is established. The lightning rod is typically connected to the grounding wire using a surge arrestor. There are additional considerations. The grounding system should be designed and installed by a qualified electrician. The number and depth of ground rods required can vary depending on soil conditions and local regulations. Periodic testing and maintenance of the grounding system is recommended to ensure its integrity. In conclusion, high-mast lighting poles require a proper grounding system to ensure lightning protection, equipment grounding, and personnel safety. The grounding system consists of ground rods, grounding wire, equipment ground conductors, and a lightning rod connection. It is essential to design and install the grounding system in accordance with industry standards and local regulations to ensure its effectiveness. Soil conditions play a critical role in the effectiveness of a grounding system. Soil resistivity, which is the measure of how much the soil resists the flow of electrical current, varies greatly depending on factors such as moisture content, mineral composition, and temperature. High soil resistivity increases the impedance of the grounding system, making it less effective at dissipating fault currents and lightning strikes. To mitigate the effects of high soil resistivity, several techniques can be employed. One common method is to use multiple ground rods connected in parallel. This effectively increases the surface area in contact with the soil, reducing the overall resistance of the grounding system. The spacing between ground rods is also important. They should be separated by a distance at least equal to the length of the rods to avoid overlapping spheres of influence. Another technique is to use ground-enhancing materials. These materials, typically composed of conductive aggregates and minerals, are used to improve the conductivity of the soil around the ground rods. They help to lower the soil resistivity and create a more effective grounding path. In areas with extremely poor soil conditions, such as rocky or sandy soil, it may be necessary to install a ground grid. A ground grid consists of a network of interconnected conductors buried horizontally in the ground. This provides a large surface area for current dissipation and helps to equalize the potential across the site. The design and installation of a ground grid require careful planning and engineering to ensure its effectiveness. Regular testing and maintenance of the grounding system are essential to ensure its continued performance. Ground resistance testing should be performed periodically to verify that the resistance of the grounding system is within acceptable limits. This testing can be performed using a ground resistance meter, which measures the resistance between the grounding system and a remote earth reference point. If the ground resistance is found to be too high, corrective actions such as adding additional ground rods or applying ground-enhancing materials may be necessary. Visual inspections of the grounding system should also be conducted regularly to check for any signs of corrosion, damage, or loose connections. Any issues that are identified should be promptly addressed to prevent degradation of the grounding system. The National Electrical Code, or NEC, provides specific requirements for grounding and bonding of electrical systems. These requirements are intended to ensure the safety of personnel and equipment by providing a low impedance path for fault currents to return to the source. Article 250 of the NEC covers the general requirements for grounding and bonding, including the types of grounding systems that are permitted, the sizing of grounding conductors, and the methods for connecting grounding electrodes. The NEC also provides specific requirements for grounding of equipment, such as motors, transformers, and switchgear. These requirements are intended to ensure that all metal parts of electrical equipment are effectively grounded, preventing them from becoming energized in the event of a fault. In addition to the NEC, local codes and regulations may also apply to the grounding of high-mast lighting poles. These codes may specify additional requirements for grounding electrode systems, ground resistance testing, and other aspects of grounding. It is important to consult with local authorities and qualified electricians to ensure that the grounding system complies with all applicable requirements. Surge arresters play a crucial role in protecting electrical equipment from voltage surges caused by lightning strikes and other transient events. These devices are designed to divert surge currents to ground, preventing them from damaging sensitive equipment. Surge arresters are typically installed in parallel with the equipment they are protecting, providing a low impedance path for surge currents to flow to ground. When a surge occurs, the surge arrestor activates, clamping the voltage to a safe level and diverting the surge current away from the protected equipment. Surge arresters are rated based on their maximum continuous operating voltage and their surge current capacity. The maximum continuous operating voltage is the highest voltage that the surge arrestor can withstand continuously without degradation. The surge current capacity is the maximum surge current that the surge arrestor can safely divert to ground. When selecting a surge arrestor, it is important to choose a device that is appropriately rated for the voltage and current levels of the electrical system. The surge arrestor should also be installed in accordance with the manufacturer's instructions and all applicable codes and regulations. Proper bonding is essential for creating a safe and effective grounding system. Bonding refers to the process of connecting all metal parts of an electrical system together to create a low impedance path for fault currents. This includes bonding the metal enclosures of electrical equipment, metal conduit, and other metal structures. The purpose of bonding is to ensure that all metal parts are at the same electrical potential, preventing voltage differences that could create a shock hazard. Bonding is typically accomplished using bonding jumpers, which are short lengths of wire that connect the metal parts together. Bonding jumpers should be sized in accordance with the NEC and should be securely connected to the metal parts using appropriate connectors. In addition to bonding, it is also important to ensure that the grounding electrode system is effectively bonded to the building's metal water pipe. This provides an additional path for fault currents to return to the source and helps to equalize the potential between the grounding system and the water pipe. The bonding connection to the water pipe should be made within 5 feet of the point where the water pipe enters the building. Regular inspections of the grounding and bonding system should be conducted to check for any loose connections, corrosion, or damage. Any issues that are identified should be promptly addressed to ensure the continued effectiveness of the system. The size of the grounding conductors used in a grounding system is determined by the size of the largest ungrounded conductor in the electrical system. The NEC provides tables that specify the minimum size of grounding conductors based on the size of the ungrounded conductors. These tables take into account the ampacity of the ungrounded conductors and the type of material used for the grounding conductors. Grounding conductors should be made of copper or aluminum and should be protected from physical damage. They should also be installed in a manner that minimizes the risk of corrosion. The grounding electrode conductor is the conductor that connects the grounding electrode system to the equipment grounding bus in the electrical panel. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. The NEC provides tables that specify the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. The grounding electrode conductor should be made of copper or aluminum and should be protected from physical damage. It should also be installed in a manner that minimizes the risk of corrosion. Grounding electrodes are the metal objects that are used to establish a connection to the earth. The NEC recognizes several types of grounding electrodes, including ground rods, ground plates, and metal water pipes. Ground rods are the most common type of grounding electrode. They are typically made of copper or copper-clad steel and are driven into the ground to a depth of at least 8 feet. Ground plates are flat metal plates that are buried in the ground. They are typically made of copper or galvanized steel and should have a surface area of at least 2 square feet. Metal water pipes can be used as grounding electrodes if they are in direct contact with the earth for at least 10 feet. The water pipe should be metallic and should not have any insulating joints or sections. When using a metal water pipe as a grounding electrode, it is important to bond the water pipe to the grounding electrode system to ensure that it is effectively grounded. The location of the grounding electrodes is important for ensuring the effectiveness of the grounding system. Grounding electrodes should be located as close as possible to the electrical service entrance and should be installed in an area where the soil is moist and conductive. Grounding electrodes should also be protected from physical damage and should be accessible for inspection and testing. The spacing between grounding electrodes is also important. Ground rods should be spaced at least 6 feet apart to avoid overlapping spheres of influence. Ground plates should be spaced at least 8 feet apart to avoid overlapping spheres of influence. The depth of the grounding electrodes is also important. Ground rods should be driven into the ground to a depth of at least 8 feet. Ground plates should be buried at a depth of at least 2.5 feet. The resistance of the grounding system is a measure of how effectively the grounding system is connected to the earth. The lower the resistance, the more effective the grounding system will be at dissipating fault currents and lightning strikes. The NEC recommends that the resistance of the grounding system should not exceed 25 ohms. If the resistance exceeds 25 ohms, additional grounding electrodes should be installed to reduce the resistance. The resistance of the grounding system can be measured using a ground resistance meter. This meter injects a small current into the grounding system and measures the voltage drop across the grounding electrodes. The resistance is then calculated using Ohm's law. Regular testing of the grounding system is essential to ensure that it is functioning properly. Ground resistance testing should be performed at least annually and after any modifications or repairs to the electrical system. The results of the ground resistance testing should be documented and kept on file. If the ground resistance is found to be too high, corrective action should be taken to reduce the resistance. These actions may include adding additional grounding electrodes, improving the soil conductivity around the grounding electrodes, or repairing any damaged or corroded connections. In addition to ground resistance testing, visual inspections of the grounding system should also be conducted regularly. These inspections should check for any loose connections, corrosion, or damage to the grounding electrodes or grounding conductors. Any issues that are identified should be promptly addressed to prevent degradation of the grounding system. High mast lighting poles are often located in exposed areas where they are susceptible to lightning strikes. Lightning strikes can cause significant damage to electrical equipment and can also pose a safety hazard to personnel. A properly designed and installed grounding system is essential for protecting high mast lighting poles from lightning strikes. The grounding system should provide a low impedance path for lightning currents to flow to ground, minimizing the voltage rise on the pole and reducing the risk of damage. The grounding system should also be designed to withstand the high currents associated with lightning strikes. This may require the use of larger grounding conductors and more robust grounding electrodes. In addition to the grounding system, surge arresters should also be installed to protect sensitive electrical equipment from voltage surges caused by lightning strikes. Surge arresters are designed to divert surge currents to ground, preventing them from damaging the equipment. The surge arresters should be installed as close as possible to the equipment they are protecting. Regular maintenance of the grounding system is essential for ensuring its continued effectiveness. The grounding electrode should be inspected regularly for corrosion and damage. The grounding conductors should be checked for loose connections and physical damage. The ground resistance should be tested at least annually to verify that it is within acceptable limits. Any issues that are identified should be promptly addressed to prevent degradation of the grounding system. Soil conditions can have a significant impact on the effectiveness of a grounding system. Soil resistivity, which is the measure of how much the soil resists the flow of electrical current, varies greatly depending on factors such as moisture content, mineral composition, and temperature. High soil resistivity increases the impedance of the grounding system, making it less effective at dissipating fault currents and lightning strikes. In areas with high soil resistivity, it may be necessary to use special techniques to improve the soil conductivity. These techniques may include adding ground-enhancing materials to the soil, installing a ground grid, or using deep-driven ground rods. Ground-enhancing materials are substances that are added to the soil to improve its conductivity. These materials typically contain conductive minerals and chemicals that help to reduce the soil resistivity. A ground grid is a network of interconnected conductors that are buried in the ground. The ground grid provides a large surface area for current dissipation and helps to equalize the potential across the site. Deep-driven ground rods are ground rods that are driven into the ground to a depth of 50 feet or more. These rods tap into lower layers of soil that are typically more moist and conductive. The costs of installing and maintaining a grounding system can vary depending on the size and complexity of the system. The costs will also depend on the soil conditions and the local regulations. It is important to obtain quotes from multiple qualified electricians before selecting a contractor to install or maintain the grounding system. The cost of the grounding system should be considered as part of the overall cost of the high-mast lighting project. A properly designed and installed grounding system is an essential investment in the safety and reliability of the lighting system. Ignoring grounding requirements can lead to serious consequences. Firstly, failure to properly ground high-mast lighting poles can create a significant safety hazard for personnel who come into contact with the poles. If a fault occurs in the electrical system, the metal parts of the pole can become energized, posing a risk of electric shock. Secondly, inadequate grounding can also increase the risk of damage to electrical equipment. Voltage surges caused by lightning strikes or other transient events can damage sensitive equipment if they are not properly diverted to ground. Thirdly, improper grounding can also violate local codes and regulations. Many jurisdictions have specific requirements for grounding of electrical systems, and failure to comply with these requirements can result in fines or other penalties.